Now, let's come to why we have been studying linear dependence and independence, linear combination of vectors. That is to tell how vectors are oriented in space with respect to each other. So the first perspective that we will give to this discussion is of collinearity. Let's see how this knowledge or how the knowledge of these terms or the familiarity with these terms that you have just seen actually help you in determining whether 2 or 3 vectors or whatever it is, they are collinear or not. Let's look at these points. I would like to put the first point here, and we won't be going into the in-depth proof of these points. You can always prove them, but the fact of the matter is they're more importantly required to be remembered by you. So, coming to the first point, and that is 2 collinear vectors are always linearly dependent. Extremely important statement. So if I take 2 vectors, they have to be linearly dependent. So let these be my vectors AB bar and BC bar. As you can see, they lie along a straight line. We already know if AB bar is a vector and if it's collinear to some BC bar, then they can be related by some lambda, right? This lambda can be any real number. So AB bar, and of course, like lambda cannot be 0 if your AB bar is non-zero, right? That's very obvious, it's not possible. So AB bar minus lambda BC bar is equal to 0. Now if you look at this carefully, this is like a linear combination of vectors only, where your first vector is this. So AB bar into 1 plus minus lambda into BC bar is equal to 0, right? This is a linear combination of vectors because you have a vector, you have another vector, and then you have 2 scalars and you're equating it to 0. Now as you can see, you have 2 scalars which are not equal to 0. What does this mean? AB and BC are linearly dependent, right? Because if they were independent, then AB bar plus BC bar could have been 0 only when you multiply them with 0, right? Then you could say that okay, they were linearly independent. But as you can see here, they are still 0 even if I am multiplying them with non-zero quantities. This lambda is not equal to 0, 1 is not equal to 0, right? That means 2 collinear vectors are always linearly dependent. That is the first important point that you need to remember. And obviously I can just write the thing which can be inferred from this. 2 non-collinear vectors are always linearly. Can you guess it? Yeah, it should be independent. 2 collinear vectors are dependent and 2 non-collinear vectors are linearly independent. Collinear vectors are dependent and non-collinear vectors are independent. And how can you prove the second point? Now the second point is very simple. Because your 2 vectors, if AB bar and BC bar, if they are not collinear, then they can't be related by some lambda, right? They can't be related by any lambda. So basically, you have some x1 into AB bar plus x2 into BC bar. You take a linear combination, you equate it to 0, and your AB bar is equals to minus x2 by x1 BC bar, right? Now, if they are linearly independent, that means both of them have to be 0. In fact, you can't have any non-zero x1 and x2, right? You can't have any non-zero in x1 and x2. Because if you end up having any non-zero x1 and x2, that would mean that your combination is linearly dependent, right? And also it would mean that you could actually relate them by some lambda BC. So that means they would become linearly dependent and they would be collinear. But now, because from the beginning itself it's clear that okay, both of them have to be 0 only if you are equating it to a 0, right? Both of them have to be 0, they can't be non-zero. So that means they obviously can't be related by some lambda, because this expression would have no meaning then. So if they are to be 0 and only 0, that means they are linearly independent, and that would mean they can't be related by some lambda. That would mean that they are not collinear. So 2 non-collinear vectors are linearly independent. Coming to the third point now. So coming to the third point, regarding collinearity. We saw that if the vectors AB bar and BC bar, if you had two vectors, the vectors collinearity could be dealt with by telling that, okay, if these two vectors are linearly dependent, they are collinear. If they are linearly independent, they are not collinear. But what if I don't talk about these vectors, but if I talk about these points A, B and C? How can I say whether these points are collinear or not? The previous two properties dealt with two vectors being collinear or not. Here I'm dealing with 2 points being collinear or not. So for that also, what I'll do is I'll take the position vector of these points and I will write a property here. I won't be proving that property, but I'll just be writing it. This is A bar, your first vector. This is your B bar, second position vector, and this is C bar, third position vector. Right. So remember, I'm taking the position. What is this? This is your origin, right? And you guys already know the vector which starts from the origin and goes to the point of interest is basically the position vector of that point, right? So now I can say that 3 points A bar, B bar, C bar are collinear if there exists x, y, z not all 0. Now pay attention to every term here and I'll actually underline everything that's important, such that the condition number 1 is xa bar plus yb bar plus zc bar is equal to 0. Number 2, x plus y plus z is equal to 0. Right. So let's actually dig into this property. It says I have 3 points A, B and C, right? What is ABC? ABC is your position vector of the points, right? They are not your vectors AB bar or BC bar directly, right? They are your position vectors, right? And they are collinear if there exists XYZ such that they are not all 0. So the first condition is you're taking a linear combination, obviously, again, right? You're taking a linear combination of which 3 vectors now? Which 3 vectors? These 3 position vectors, right? You're taking a combination of these 3 position vectors and you're equating that to 0 and saying this expression has to be 0 such that x, y, z are not all 0 together. What does this mean? This means that A, B, C should be linearly dependent. That is the first condition. That is the first condition. Why? Because if they were not linearly dependent, then the condition would have said that all x, y, z should be 0. But here it's saying that not all are 0. That means at least one of them have to be non-zero. And this expression should still be 0. What does that mean? That means that this combination, these 3 vectors A, B, C have to be linearly dependent. But that's not enough. With that, I can't say that it's collinear. This second condition also must hold good. These scalars must add up to 0. So if your scalars are adding up to 0, and also these vectors, these position vectors are linearly dependent. The first condition is position vectors should be linearly dependent. Second condition is scalars sum up to 0. If both of them are taken care of, then I can say that these 3 points are collinear to each other, right? In fact, this property also can be proven if you actually consider, this dividing in the ratio m is to n or something and applying section formula. The proof is actually coming from section formula. I don't want to put that proof here, but I just want you to actually remember this result as it is, because it will be helpful directly in the examination, because when you come across such question, the options themselves will give you an idea that you have to use this property to actually evaluate the answer that's required. So you can obviously use section formula to prove this. I leave that to you. But for now, with this we complete all the topics, all the 3 properties that you needed to know as far as collinearity under the umbrella of linear combination of vectors is concerned. We've already seen collinearity before, but here what we saw is how this linear combination of vectors can actually help you understand whether the vectors are, or the position vectors regarding certain points, the points are collinear or not, right? So with this, let's move on to the next subtopic, and that's coplanarity under the umbrella of linear combination of vectors. Now let's come to discussing coplanarity under the umbrella of linear combination of vectors. As you can see here, there is a plane there is this green plane and there are all vectors in the plane. I've drawn some vectors in the plane. This means that these three vectors are coplanar. Sometimes it might also happen that this C bar that you see here, instead of being like this, it might just point out of the plane like this. So in that case, these three won't be, this is some angle theta, right? So it might just point out. So in that case, all these three won't be coplanar. Now let's see how can we actually know whether the three vectors are coplanar or not. That is with the help of these properties. Three coplanar vectors are always linearly dependent, right? Three coplanar vectors are always linearly dependent. So if you compare this with collinearity, there it was two linearly dependent vectors, two collinear vectors were linearly dependent, right? So that there were two collinear vectors which were linearly dependent. Here I'm talking about, whenever I talk about coplanarity, I talk about three coplanar vectors. Why? Because if you take two vectors, any two vectors, you can always draw a plane through them, right? You take any two vectors, any direction, any magnitude, you can always draw a plane through them. So just like from one point, infinite number of lines can pass, right? And from 2 points, one line can pass, right? So from 1 point, infinite number of lines can pass. So just the way those are facts, similarly here, when I draw two vectors, I can always make them pass through a plane. It's always possible, right? That will always happen. Just the way I can always pass a line from 2 points, I can always pass a plane from two vectors. The problem comes when there is a third vector. Now whether the third vector lies in the same plane or outside the plane, that is determined with the help of these properties. So three coplanar vectors. So when I talk about coplanarity, I talk about three. When I talk about collinearity, I talk about two. Notice that difference. So three coplanar vectors are always linearly dependent, right? And this I'm again not proving. Just extend this understanding from your collinearity. Just the way two collinear vectors were linearly dependent. Here, if these three vectors that you see here, A, B, C, if they are in the same plane, if they are coplanar, then these three have to be linearly dependent. What does that mean? That means I must have scalars not all zero, such that my linear combination is zero. I must have at least one non-zero, this xyz. At least one of these xyz should be non-zero, and this equation should still be valid, right? Then I can say that okay, they are linearly dependent. So that means three coplanar vectors, according to this property, this A, B, C must be linearly dependent. And if any of your C, A, B or C, if anything just becomes non-coplanar, right? So three non-zero, first of all they have to be non-zero, remember this, right? Because if they are zero, then there is no point in talking about its coplanarity or anything. The linear combination will be zero if they are all zero, right? So three non-zero and non-coplanar vectors are always linearly independent. Coplanar are linearly dependent, non-coplanar are linearly independent. So if your C is actually pointing out of this plane and it's not coplanar with A and B, right? That means this A, B, C are linearly independent. That means XA bar plus YB bar plus ZC bar can be equal to 0 plus ZC bar can be equal to 0 only when this XYZ are all 0, right? So I hope you're able to see the connection here. I'm talking about their orientation. I'm saying they are non-coplanar. They are not in the same plane. And I can actually tell that by looking at this linear combination. This linear combination can be 0 only when x, y, z are all 0. Right? Even if you have one of them non-zero, then they will become linearly dependent and then they will become coplanar. Then you can't have them like this. Then you'll have to have this C in the same plane. Right? So that's the interesting part here. That's how algebra is being related to the orientation, to the geometry of the vectors, right? So three non-coplanar, non-zero vectors are always linearly dependent. And one more important point that's not really coming under the coplanarity of 3.3 vectors here, that is more than 3 vectors are always linearly independent. So if I have A bar, B bar, C bar, D bar, right? If I have vectors like this, then more than 3 vectors are always linearly independent. That means you can make this combination x, y, z, w 0 only when all your x, y, z, w's are all 0. So through more than 3 vectors are always linearly dependent. So they should actually not be all 0 at once.